A modern aircraft carrier weighs more than 100,000 tons. So how does something that heavy ever leave the dock without sinking? Its flight deck is smaller than 5 football fields. Yet planes land on it doing over 150 miles an hour, dozens of times a day. Somewhere below that deck sits a nuclear reactor small enough to hide inside a school bus, and it can run for 25 years without ever being refueled. None of this should be possible with steel, rivets, and human hands. So how do you actually build a floating city that can survive a war? Let's step inside and find out. Building an aircraft carrier takes over 5 years, a workforce of thousands, and more steel than the Eiffel Tower. Cut, bent, and welded into a machine that has to work perfectly the first time, every time, for the next 50 years. So how do shipbuilders turn raw steel into the most powerful warship on the planet? Let's step inside and find out. A carrier's hull isn't built like a normal ship, bow to stern. It's built like a puzzle, in pieces, upside down, in a building bigger than most airports. It starts with raw steel plate, some of it 4 inches thick, delivered by rail to a shipyard the size of a small city. Before a single piece touches water, workers cut and shape the steel into modules. Self-contained chunks of ship, some as large as a 3-story building and weighing over 900 tons each. And some of that steel is treated with special coatings to resist saltwater corrosion for decades, since the ship will spend most of its life sitting in the harshest environment on Earth, the open ocean, day after day for 50 years straight. Each module is built separately, often simultaneously, in massive assembly bays. Engines, wiring, plumbing, and even paint are installed inside the module before it ever leaves the shed. Because once it's welded into the hull, some of that space becomes almost impossible to reach again. A giant gantry crane, one of the largest land-based cranes on Earth, lifts each finished module, sometimes over 1,000 tons, and lowers it into place with a tolerance of just a few millimeters. Workers then weld the modules together, seam by seam, forming a hull that eventually stretches over 1,100 feet long. A single misaligned module, off by even a few centimeters, can throw off the fit of everything built on top of it. So shipbuilders use lasers and 3D scanning just to confirm every module lines up before a single weld is made permanent. Some modules are engineered with so little margin for error that workers joke this ship leaves less room for mistakes than a spacecraft does. Welders work around the clock in shifts, running seams that stretch for miles when you add them all together. And every single weld is X-rayed or ultrasonically scanned afterward to check for hidden cracks. Because a flaw buried inside a seam might not show itself until the ship is thousands of miles from the nearest port. Inspectors sign off on each joint individually before the next module is allowed to go on top of it. By the time the hull is finished, it's no longer really a ship in the traditional sense. It's dozens of pre-built neighborhoods of a floating city fused into a single steel shell ready for its heart. A hull that size needs a heart that never runs out of breath. 2 nuclear reactors, each smaller than a shipping container, will power this entire vessel for a quarter century without refueling. Enough energy to run a small city, packed into a space you could walk across in 10 steps. The reactor components are built off-site, in specialized nuclear facilities under extraordinary security, then transported to the shipyard as sealed, pre-assembled units. This isn't something built on the open shop floor. It's installed as a self-contained unit, lowered into the hull before the upper decks close it in forever. The reactor compartment is surrounded by layers of shielding, protecting the crew even when they're working just a few decks from an active nuclear core. Inside each reactor, enriched uranium fuel generates heat through controlled nuclear fission. That heat turns water into steam, and the steam drives turbines that do 2 jobs at once: spin the massive propeller shafts and generate electricity for the entire ship, from radar systems to the toasters in the galley. Because the reactor sits so deep in the hull, engineers install it before the decks above are sealed. There's a narrow window, sometimes just weeks, where the reactor can go in before it becomes physically impossible to lower it into place. Once installed and sealed, that reactor may never be removed for the entire 50-year life of the ship. Engineers essentially have one shot to get the installation right, because start over isn't an option once the deck goes on top of it. Every pipe, valve, and pump connected to the reactor system goes through its own separate inspection process, and specialized technicians spend months just certifying the welds around the reactor compartment. Because this is the one part of the ship where a mistake can't simply be patched later, it has to be right the first time. With power and propulsion sealed inside, the carrier now has something no cargo ship or cruise liner will ever have: the ability to sail around the world more than a dozen times without stopping to refuel. A heart that never stops is useless without a deck that can survive being hit over and over by 40-ton jets. Every landing on that deck is technically a controlled crash, and the deck has to survive thousands of them without cracking. Pilots call landing on a carrier controlled crashing for a reason. There's no gradual touchdown, no easing onto the runway. The jet slams down at full power, ready to take off again instantly if the tail hook misses every single wire. The flight deck isn't ordinary ship steel. It's a specially hardened alloy plate engineered to absorb repeated high-speed impacts, jet blast heat that can exceed 1,000 degrees Fahrenheit, and the constant abrasion of aircraft tires and arresting gear. Workers weld the deck plates across the top of the hull in enormous sections, then embed a network of steel cables underneath, the arresting wires, connected to hydraulic engines below deck. When a jet lands, a tailhook catches one of these cables, and the hydraulic system absorbs the aircraft's momentum, stopping a 40-ton jet from over 150 miles per hour to a complete stop in about 2 seconds. On the opposite end, catapult tracks are embedded into the deck itself, steam or electromagnetic systems capable of flinging that same jet from 0 to 165 miles per hour in roughly 2 seconds, using a runway shorter than a city block. The margin for error on the arresting wire system is almost nothing. The cable has to catch the tail hook within inches, on a deck that's pitching and rolling with the ocean, in wind at night, with the pilot unable to see the deck until the final seconds. Below the flight deck, a hangar bay runs almost the length of the ship, connected to the surface by deck edge elevators, capable of lifting a fully loaded fighter jet in seconds. Every one of those elevators has to be tested under full load, in rough seas, before a single aircraft is trusted to ride on it. Once the deck, catapults, and arresting gear are tested and calibrated, the carrier can now do something almost no other vessel on Earth can: turn open ocean into a functioning airport. An airport needs a control tower, and on a carrier, that tower is one of the most crowded rooms in the entire ship. The island, that tower rising above the flight deck, looks small from a distance, but it's actually packed with more radar, sensors, and communication systems than most military bases. The island is one of the last major modules lowered onto the hull, built separately and craned into place once the flight deck is complete. It houses the bridge, air traffic control, and the ship's most advanced radar and defense systems. From up there, air traffic controllers coordinate dozens of aircraft launching, landing, and circling overhead, all within the same tight airspace, often at night, often in bad weather, with zero room for miscommunication. Once the island is in place, crews begin the enormous task of fit out, running over 1,600 miles of electrical cable throughout the ship, installing plumbing for thousands of crew members, building galleys capable of feeding 5,000 people 3 meals a day, and wiring the combat systems that link radar, weapons, and aircraft into a single coordinated network. Every system, from the elevators that move jets from the hangar to the flight deck, to the desalination plants that turn seawater into drinking water, has to be tested individually, then tested together before the ship is ever allowed near open water. Before the carrier even leaves the shipyard, it undergoes what's essentially a full-scale rehearsal of war, testing weapon systems, aircraft launches, and emergency drills. Because once it's deployed, there's no dry dock nearby to fix a mistake. During sea trials, the ship pushes itself to the edge of its limits on purpose. Sharp turns at high speed, emergency stops, simulated power failures, all to prove that a system built by thousands of different hands over 5 years actually behaves as one single, coordinated machine when it matters most. After more than 5 years of construction, sea trials confirm the ship is ready. A vessel that started as flat steel plate is now a self-sufficient, nuclear-powered airbase capable of operating anywhere in the world for the next half-century. Thousands of welders, electricians, pipe fitters, and engineers will spend their entire careers on a single hull, building a machine designed to outlast them, sailing for half a century on the strength of steel plate, nuclear fuel, and a level of precision most of us will never see up close. That's how a stack of raw steel plate becomes a 100,000-ton nuclear-powered airport, built piece by piece, tested system by system, until a ship that shouldn't be possible is finally ready to sail. Precision, scale, and engineering most of us never think about, until now.